point of this tutorial is to take another look at Bohr's model of the atom and give a little background as to why he did what he did to come up with the idea of electrons only being found in certain energy levels and energy being given off in the form of photons when they go from one energy level. Besides that background, then we're going to look at what Bohr did not know at the time, and that's a theoretical underpinning for his assumptions. And that's going to take us to de Broglie, which really came about 10 years after Bohr's initial models that seemed to solve a few problems. This tutorial is mostly derivations. The main outcome are the equations that go with it, which are a few, and then we will do some work in class as to look at what exactly are you supposed to know about it. So what we're going to do is appreciate how we can take some of the known physics, especially electrostatics, to a certain extent, the Rydberg uncertainty principle, and come up with a model that worked fairly well. They got us a good start, and stuff that we've already talked about in terms of the Bohr model. Okay, so background. It had been known since the mid to late 19th century, so we're talking 20, 30 years, that the emission spectrum of hydrogen, okay, especially hydrogen, all right, followed a particular mathematical pattern. Okay, different people, Balmer, Lyman, Paschen, had discovered different series of emission spectra, colors, and they found that they follow the following formula. If you take the inverse of the wavelength, it's equal to some constant times 1 over n squared minus 1 over small n squared, where both n's are integers based on a particular series. So the Balmer series might be 2 for big N, 1 for little n, 3 then 2, 4 then 2, 5 then 2. I don't remember the specifics. But each in their own found that they followed the same pattern, and the R was just nothing but a constant called the Rydberg Constant, named after a physicist who had come up with its value experimentally. Okay? The problem with this was no one, not even Rutherford after he did his nuclear model, could explain the physical basis for this pattern. Okay, or the meaning of R. It worked, it explained hydrogen, but no one knew why. And this is where Bohr picks up the problem in around 1911 or so. Okay, so we've talked about this a little bit, but like I said, I'm going to go into a little bit more detail. So he wants to take a quasi-quantum approach. So again, by this time, it's been 10 years since Planck's idea of light being quantized to explain the black body radiation. 1905, Einstein used the same idea of quantized light to explain the photoelectric effect. So Bohr is pretty much well versed in this idea that certain things seem to be quantized. So he said, perhaps this would explain why we get distinct colors for the hydrogen atom. All right, but he needs something physical that needs to be quantized about the electron's orbits. Okay, so in other words, if you think of the individual colors that comes from a particular atom as distinct amounts, that implies quantization, but what would be quantized in an atom? All right, so you can think of all the parameters of an atom that might come in incremental values, and Bohr hit upon something that worked. And that's something, if you stop and think about the solar system model, I'll give you a chance to think about it. So here's a nucleus, and we're envisioning electrons going in orbits. So what might be something that is quantized about those orbits? Well, one thing that might pop to mind is radius, okay, and that turns out to be true. And we eventually talk about energy levels, but you need something about the motion. So if I go round and around and around, what might be something about the motion that's a fundamental aspect of that? Something we learned last year, probably forgotten about, and it turns out that it's angular momentum. Okay, and that was his stroke of genius, to say, all right, if we quantize angular momentum, we can explain these transitions and these colors. So I'm going to take that idea and run with it, at least as far as we can get in the 15 minutes. Okay, so recall angular momentum for a single mass in orbit. So if I got something and something's going around, right, like this with a velocity v, it has a mass m. How do we calculate its angular momentum? Well, the symbol for angular momentum is L, and if you recall, it's really the cross product of its momentum times how far away from its pivot point. Well, that all translates to m times v, there's the momentum part, times r, there's the lever arm part. Okay, so this is supposed to be an arrow, and we are some distance r away from the pivot point. Now, what did Bohr do? He applied it to hydrogen. Now he wants to quantize this. So what he basically said is that if you take the angular momentum of any electron, mvr, in an orbit around a hydrogen atom, it's going to be equal to n times, oops, that's supposed to be n. So n is a number, there's your quantized part, times h, there's Planck's constant, divided by 2 pi, okay? And n is the energy level, okay? And that's either 1 or 2 or 3 and so on. That's the, like I said a second ago, the quantization part. He doesn't have any basis for saying this. It works, okay? And when you quantize angular momentum, it leads to a quantization of the radius of the orbits as well as the energy. And that's what I'd like to show in the space below, and then we'll come up with the final result in the box you see to the right. So you can pay attention to this, you can faithfully copy it, but try to understand what we're doing. So I'm going to actually do 2 derivations. We'll do one for the radius, and then that's going to lead to one for the energies. So I'm going to start over here for radius. How can we use this idea? Okay, I'm going to rewrite it right here since I'm below the screen, that mvr equals nh over 2 pi. All right, well, he's going to still follow some classical rules of physics. If I've got an electron in orbit, there's got to be some force holding in orbit. That force would be the electrostatic force. So I have the electrostatic force is making it move in orbit. That orbit's a circle, so the circle is going to follow the centripetal rule. So I'm going to have mv squared all over r. Okay, how do we calculate the electrostatic force? Well, that's going to be Coulomb's constant times the charge of the electron times the charge of the proton, which are both the same value, which we're going to call E instead of Q for elementary charge. And since there's 2 of them, E squared, all divided by the distance squared apart. So there's Coulomb's law, and that's going to equal mv squared all over r. All right, so if I rearrange this, I can solve for r. I'll let you do the math on this or the algebra, and that turns out to be k times E squared all over mv squared. All right, now we can use his assumption that the angular momentum is conserved, or excuse me, not conserved, but is quantized. So if I take this equation here and rearrange it, I can say, and I'll do it down here, where V must be, so I'm going to solve this equation for V, and I see that's equal to N times H all over 2 pi M times R. If I substitute it into this equation below, I have R equals K E squared. Now I'm dividing by V squared, so I'm going to do that all. I'm going to substitute this whole thing in, squared it in one term. I'm not going to bother with all the little algebraic steps. I trust you can work that out for yourself. Okay, so that becomes K squared 4 pi squared times M R squared all over N squared H squared. Okay, so this is a big awful mess. And also I have R's on both sides, so I'm going to do one other step. This R cancels out with this R squared. So I'm going to move everything else to the left side, leaving me with R equals, okay, so basically numerator and the denominator flip, N squared H squared all over K, Coulomb's constant, times the charge is squared, 4 pi squared times M, the mass of the electron here, okay? So there's our first derivation. So we can plug in various values for N. So if I want the first energy level, N is 1, I take H squared divided by this whole mass, I will get an idea of how big the first orbital is. And then if I put in 2, I see that it goes up by the square of N, and he could recreate that. So that was wonderful. Even better, he could state something about the energies. All right, so this gives us a nice review of total energy. So let's look at, for the next derivation, the total energy of an electron at a particular orbital. Okay, again, using this quantized idea. So remember, total energy, sigma E, is the sum of the kinetic energy of the electron by virtue of motion, moving, plus whatever potential it is. And it's going to be electric potential because of the attraction between the proton and the electron. So let's look at each one in turn. So the kinetic energy, we know, is 1/2 mv squared. And we're going to use this relationship right here to manipulate this. In other words, I can see that mv squared right here is equal to k. If I bring the r, this r over to this side, I've got this cancels out, this cancels out. So that's equivalent to Coulomb's constant times the square of the charges divided by how far away they are. Okay, so it's a simple little substitution worth knowing how to do. We've kind of done this before with gravity. Potential energy, it's electric potential energy. So electric potential energy is going to be equal to the voltage between the two multiplied by the charge of one of them. In other words, Q times delta V, and delta V is going to be KQ over R. Go back to your reference tables, look back up the equation or the definition of voltage to verify this. So when I put the two together, I get negative, potential energy is going to be negative here because they're attractive, or one is positive, one is a negative charge, K Q squared or E squared all over R. Okay, it's a fairly simple equation. And again, it's something you need to know. It's fundamental to electrostatics. So this total energy, therefore, is the sum of these two, K E squared over, oh, I forgot the 1/2 here, my bad, 2R minus K E squared all over R. Okay, my common denominator is 2R. Subtract them, and I get my total energy is equal to negative K E squared all over R. Okay, oops, my bad, over 2R. That negative is important. Okay, that tells us that the total energy is negative, therefore the electron is bound to the atom. Something we already know, but here you can reproduce it. Now we're going to bring in, this is a general formula. Now let's bring in what he assumed about the angular momentum. So things are going to get a little bit messy. So if I substitute in our velocity, so I've got a, if I substitute in our R equation into right here, I will get this mess where it says that the total energy, I'm just going to write that as E right now, at some quantum level is equal to, so I'm going to do this all in one step and then break it up, negative 4 over 2 pi squared K squared E to the 4th times the mass of an electron all over N squared times H squared. Okay, let me rewrite that a little bit differently, and I'm just about done. Negative 4 over 2, so this becomes negative 2 pi squared K squared E to the 4th M all over H squared times 1 over N squared. I'm just separating out there. And there you go. There is Bohr's reproduction of the fact that the energy level, which is really 1 over lambda, right, by Planck's law, is proportional to 1 over the square of the quantum number, the energy level. This is what Lyman and Balmer and Paschen found experimentally that no one could explain theoretically. So Bohr comes up with a value that is very, very important because it matches experiment very, very nicely. In fact, if you look at this whole mess right here, and you plug in all these values, Coulomb's constant, the charge of an electron, the mass of an electron, and Planck's law, and you do it in electron volts, because these have to all come out to be units of energy, because N is a dimensionless number, and we're solving for energy, it turns out that the equation is negative 13.6 eV, all divided by N squared. And I'm hoping you recognize that that 13.6 is nothing more than the energy of an electron when it's in the ground state. In the ground state, N is equal to 1. So Bohr is able to reproduce the numbers beautifully for hydrogen. Okay? All on the supposition that angular momentum is quantized. He had no basis for saying that from theory, but he knew he was on something because it matched the data very, very nicely. If you were to put in 2 for this, the second energy level, 2 squared, 13.6 divided by 4, should give us the energy level of the second one that we've seen in our reference tables. Okay? So what we'll do in the class tomorrow, before we apply this, is look at what basis, is there any theoretical basis to assume that angular momentum is quantized? And the answer is yes, but it came later, and it came from de Broglie's idea of electrons being just as much waves as they are electrons.